Hey everybody, welcome back. This is our quick video guide on how to do a hand calculation for a one-way ANOVA. Remember, you can always download the PowerPoint and follow along with me, so let's get started. I've tried to summarize the formulas that you will need for a one-way ANOVA in this slide. You can see that this line mirrors what the SPSS output looks like as well. You have your sum of squares in the first column, the degrees of freedom in the second, the mean squared in the third, and then the final column only has our F ratio. You can also see that our first row is for the between, our second row is from within, and the last one is our total. It's important that we're keeping up with what all of our mathematical shorthand means. So for example, this here, SSB, is the sum of squares between. Anytime you see the SS there, that's going to be sum of squares. So we have the sum of squares between and the sum of squares within. The sum of squares total, the formula for that is the same way you find the total for anything. It's the between plus the within. We also have our degrees of freedom. Now for an ANOVA, there are some extra versions of degrees of freedom. You should already be familiar with this one, n minus 1. So that is the number of people in the study minus 1. But we have two others. We have our degrees of freedom with between and our degrees of freedom within. For that, again, you have your n, but you have a new symbol, which is k. K is the total number of treatment conditions. Think of this like groups. How many groups are there? How many conditions are there in the study? That's going to be K. So however many groups there are minus 1 is the degrees of freedom between. The total number of people minus the number of conditions is the degrees of freedom within. Then we have our mean squared. You have our mean squared between and our mean squared within. You can see that the formula just takes the preceding two cells and divides them. So the sum of squares between divided by the degrees of freedom between gives us the mean squared between. For the mean squared within, we take the next two cells, the two cells that are in front of it, the sum of squares within divided by the degrees of freedom within. And then to find our F ratio, we just divide those two things. It is the mean squared between divided by the mean squared within. So this is all presented for you in an accessible chart. The next slide actually has an image slide if you want to take it out of the PowerPoint and save it, whichever one's easiest for you to use. But those are going to be the formulas we're going to work with. So for ANOVAs have 4 steps. We need to have all of the sum of squares, so we need the between, within, and total. We need to fill in our degrees of freedom. So we need, again, between, within, and total for the degrees of freedom. We have to find our two mean squared, the between and within. And then the last step is we divide for the F ratio. Here's just, again, a repeat slide with our formulas organized for you. This way, again, you have several areas where you can get all the formulas that you need. So let's get to our first example. You are a researcher and you're interested in which type of candle lasts the longest. And you have 3 options: non-scented candles, low-scented candles, and highly scented candles. The researcher is going to gather 4 candles of each of these 3 types and will burn them in the lab, counting the days it takes for the candle to become unable to burn any further. Candle type is going to be our independent variable, our one factor in this ANOVA. And the time burning is the dependent variable. I also give you some of the sums of squares to get you started. But before we get there, let's get to our first questions. Why is this an ANOVA, and why is this a one-way ANOVA? Well, this is an ANOVA because we have 3 levels to our independent variable, to our factor. For a t-test, we can only compare 2 things. We have 3 types of candles. So because we have 3 types of candles, we can't use a t-test. We have to use an ANOVA. I also know it's specifically a one-way ANOVA because there's only one factor. What I give you as an example here is, what if we also looked at color? So if instead we had factor A as the candle scent with the 3 levels of non, low, and high, and we added to that factor B, perhaps a candle color, and we gave that 2 levels, maybe orange and blue. If we had that, then that would be a factorial ANOVA. Specifically, it would be a 3 by 2. But again, that's just an example so you can see what a factorial ANOVA would look like in this situation. This is a one-way ANOVA because we just have one factor with 3 levels. So our first step is to make sure we have all of the sums of squares that we need. I gave you the sum of squares between and the sum of squares within in the description. So what we need to do is find the sum of squares total. Again, just like with any total, all we have to do is add that up. So go ahead and pause and do that. Did you get the right answer? The sum of squares total should be 100.92. Now, one of the things I mentioned is that on other assignments, you might be given any combination of these. If I give you the between and the within, you add them together for the total. But if I gave you the total and between, you could solve for within. If I gave you the total and within, you could solve for between. Just make sure you realize that the total, the relationship of the total is just adding the other two together. So as long as you have two of these, you can find the one you don't know. So I've started you a chart where we can organize all of the results that we have found through our calculations. As you can see, we've finished our sum of squares column. We have the between, the within, and the total. Next up is going to be the degrees of freedom. So I've summarized our formulas here. Go ahead and test yourself. See if you can come up with the answers to these. Pause the video if you need to. So for the first one, the degrees of freedom between, the formula is k minus 1. Remember, the k is the number of conditions. For this example, it's the types of candles that we used, and we used 3. So k is going to be 3. So our degrees of freedom between is 3 minus 1, which is 2. For our degrees of freedom within, that formula is n minus k. N is going to be the total number of candles that we used here. So we had 4 of each of the 3 types. That means n is 12. So we substitute in 12 minus the 3, which is the number of conditions or types of candles for this example. So our degrees of freedom within is 9. Our degrees of freedom total is n minus 1. We just found what n is, so calculate the degrees of freedom total on your own. Did you get the right answer? It's 11, because 12 minus 1 is 11. So our degrees of freedom column is now also complete. We have 2 for the degrees of freedom between, 9 for the degrees of freedom within, and 11 for the degrees of freedom total. Our next job will be to find our 2 mean squared. Here are the formulas for our mean squared. Remember, it's just taking the 2 cells that occur before the mean squared and dividing them. So go ahead, pause, and see if you can find that on your own. Did you get the right answers? Our mean squared between should be 14.085, and our mean squared within should be 8.08333 forever. So we can fill out our chart again. So your chart should start to look like this. This is just, again, a summary of all of the calculations we've done so far. Well, now we're down to our F ratio. The formula for the F ratio is to take our 2 mean squared and divide them. Between is our numerator and within is our denominator. So go ahead and pause, see what you come up with. Did you get the right answer? 1.7425. So we've filled out our whole chart, but that doesn't mean that we're done. So just like with our t-tests, there's an extra step. To calculate just the F ratio is the 4 steps I mentioned, but that just gives you the F ratio. We don't know if it's statistically significant. Just like with our t calculations, what we have to do is take that F ratio that we've calculated and compare it to the critical values in the F chart. Just like the t chart, there's an F chart. There's one in your module. There's also a video on how to use it. But for the purpose of this video, I've just included a small sample of that chart in the next slide for us to play with. All F charts have a top row that is usually labeled something like the degrees of freedom numerator. This is their version of saying the degrees of freedom between. That's because the degrees of freedom between is part of the between that is the numerator for the F ratio. The first column is the degrees of freedom denominator. That's going to be our degrees of freedom within for the same reason. Each cell of the chart will have 2 numbers. The top number is for alpha level 0.05, and the bottom number, which is often bolded, is for alpha level 0.01. So for our example, remember, our degrees of freedom between was 2 and our degrees of freedom within was 9. we go over to the column for 2 for the degrees of freedom between, and we go down to the row for degrees of freedom within for 9. And because I didn't tell you to do anything different, you're going to go with the top number for alpha level 0.05. That means the critical value for our combination of degrees of freedom is 4.26. So remember, the F distribution is asymmetrical. It swells at the beginning, crests, and then comes down into a single tail. That's why all of the values in the F chart are positive, because we're not doing two-tailed tests, only a one-tailed test. The F ratio we calculated for our candle example is 1.7425. The critical value we found from the chart, though, is 4.26. That means the boundary that marks the difference between the extreme tail where things are significant and the rest of the distribution is at 4.26. So for this example, our results are not significant. Our results, our T observed, the one that we calculated, is not greater than the critical value. Thus, it would be in the swell of the distribution and not in the extreme tail. So our results are not significant. So I made up this example so that you could see in one of our calculation videos an example of something that is not statistically significant. But there is something else that we need to cover, and that's post hoc tests. And for a post hoc test, we need it to be statistically significant. So imagine this. What if we had used different candles and it turned out that there was a significant difference? Well, knowing that your F value is statistically significant, it's greater than a critical value, is great. But it doesn't tell you which candles are actually performing better. All it says is there is a difference here. A post hoc test is what's going to tell us exactly which candles or which comparisons are significant. In the PowerPoint on concepts, I mentioned that there's like a bunch of different kinds of post hoc tests. I think the last time I counted for SPSS, there was 15 options. I only want you to know 2 versions. Chef's, which is the most conservative, meaning it's the hardest one to get a statistically significant difference in, and Tukey's. The reason why I want you to know Tukey's is that Tukey's is one of the most common post hoc tests used in the psychology field. So Tukey's is the one that we're going to hand calculate. So let's try example number 2. Let's say that researcher decided that her sample of 4 candles was too small. So she's going to replicate the study, but with 9 candles of each type. And here are the 2 charts of her findings and her new calculations. As you can see, our new F ratio is greater than the critical value. By the way, the comparison value for this new degrees of freedom combination is 3.4. So absolutely our 9.15 for our calculation is statistically significant. But again, that just tells us that there is a significant difference. We don't know where it is. The post hoc is going to tell us how to do that. So we're going to use a Tukey's post hoc test. I've included your formula here, which is HSD, which is the mathematical symbol for Tukey's post hoc test, is going to equal Q times the square root of the mean squared within divided by n. For this example, Q is going to be 3.53. I will give you Q each time. You don't need to know how to calculate it. It's a whole extra step that we don't need to bother with. So for step 1, I want you to take what you know from the previous slide with the results and this slide here with the formula and come up with what is our HSD, what is our Tukey's post hoc test value. Did you get the same answer? When you fill everything in, you should get 2.353 forever. So that's our Tukey's post hoc test result. Step 2 is now we're going to compare our averages, compare our means. This will help us find out which candles are significantly different. For the first comparison, I've done it for you, and then I'm going to let you try the other ones on your own. So our first comparison is going to be the non-scented to the low scented candles. So we take the average for the non-scent, I gave you that as 3, and the average for the low scent candle, which I gave you, is 5.44. We subtract those to get 2.44. So the difference between those means is 2.44. If the difference between your means is greater than the post hoc value, you have a significant difference. So 2.44 is greater than 2.35, which means yes, there is a significant difference here. The lower scented candles burn significantly longer than the non-scented candles. I know that because, again, the difference between the means is greater than the post hoc value, and that means that this 5.44 is significantly higher than 3. Remember, you can't just compare averages. When we do these comparisons, we're taking into things like the average, the variance, the sample size, lots of stuff. So what we're saying here is everybody knows that 5.44 is greater than 3. But with all of these things taken into account, what we're saying is that 5.44 in this specific situation is statistically significantly higher than 3, not just a little higher. So I'm going to let you do the next one. I want you to compare the non-scented candles to the highly scented candles. Again, remember what you're going to do is you're going to take the average for the non-scented candle and the average for the highly scented candle and subtract them. You compare that value to your Tukey's value to see if there is a significant difference. Pause and see what you get. Here we go. So 3 minus 7 is 4. 4, of course, is greater than our Tukey's post hoc value. So yes, there is a significant difference here. Again, the scented candles burn longer than the non-scented candles. And again, 7 is greater than 3, but it is significantly greater than 3. We only have one more comparison to do, and that's the low scent to the high scent. So go ahead and try that one now. Again, pause. So for this one, again, 5.44, the average for the low scent, minus 7, which is the average for the high scent, is only 1.56. That is not greater than our comparison value for our Tukey's post hoc, which means there is no significant difference between the low and high scented candles. Again, see, 7 is greater than 5.44, but it's not greater enough to say that it is significantly different. So the way we interpret this whole thing is the first study, example number 1, was not statistically significant because there was no statistically significant difference between the candles in the first example. There was no reason to do a post hoc. The second example, where we added more candles, turns out that was significantly different. But the F ratio doesn't tell us where the difference lies. The post hoc test does. So when we did the Tukey's post hoc test here, we compared the first to the second, the first to the third, and the second and the third to see which comparisons were significantly different. And what we learned is that there's no difference between low and highly scented candles, but both are different than unscented candles. So if you care, you should only buy low and highly scented candles, and you should not buy non-scented candles if you want them to last the longest amount of time. Now again, I made all these numbers up, so you buy whatever candles you want in real life, right? But for our example, that's how we would interpret all this. Again, I recognize that ANOVAs are much more complicated than some of the other tests that we've done. ANOVAs, one-way ANOVAs, is the last hand calculation we will do in this class. The other tests that you will learn, you're only going to learn how to interpret either their output or make judgments about them or to summarize them or interpret their results. You're not going to have to hand calculate them. So I hope this was helpful in getting you through the homework. Always remember, if you have questions, you can always reach out to me, and I'll see you online.